May 27th, 1943, 8,000 feet above the Philippine Sea. Lieutenant Commander Paul Roach squinted through the salt-crusted canopy of his TBF Avenger at the Japanese destroyer cutting through the water below. His briefing that morning had been explicit: approach at 150 miles per hour, drop the torpedo at 800 yards, and pray the Japanese gunners were slow on the trigger. It was the same suicide run that had killed half his squadron over the past 6 months. The math was brutally simple. At 150 miles per hour, an Avenger became a lumbering target that even inexperienced anti-aircraft crews could track with deadly accuracy. But torpedo physics demanded slow speeds. Drop a Mark 13 torpedo faster than 150 miles per hour, and the weapon would either break apart on impact with the water or dive so deep it would pass harmlessly beneath its target. Roach had already lost 3 wingmen to this impossible equation. Then, 2 weeks ago, something had changed. His squadron had received modified Avengers equipped with what the maintenance crews called the new pitch system. The propeller blades could now shift to angles that seemed to defy every principle of aircraft design Roach had learned during flight training. This morning's mission would test whether those impossible blade angles could break the tyranny of torpedo physics that had made every attack run a calculated sacrifice. As Roach pushed his stick forward and began his descent toward the destroyer, he advanced the throttle to settings that would have torn a standard Avenger apart. The modified propeller's blades twisted into their extreme fine pitch configuration, grabbing massive amounts of air and hurling it backward with a violence that pressed him hard into his seat. The airspeed indicator climbed past 200 miles per hour, then 250, then touched 300 as the Avenger transformed from vulnerable bomber into screaming projectile. The Japanese gunners, trained to track slow-moving torpedo planes, found themselves facing an aircraft moving twice as fast as anything they had encountered before. Their carefully aimed flak bursts exploded where Roach's Avenger should have been, but the aircraft was already a quarter mile beyond those fatal positions. At 600 yards from the destroyer, Roach pulled the torpedo release and felt the Mark 13 drop away. The weapon hit the water at a speed that should have destroyed it instantly. But the engineers at Bureau of Aeronautics had solved that problem too, strengthening the torpedo's nose cone and adding stabilization fins that could handle the brutal forces of high-speed water entry. The destroyer's captain had 3 seconds to realize his vessel was doomed before the Mark 13 struck amidships with the force of 1,500 pounds of Torpex explosive. Roach pulled his Avenger into a climbing turn and keyed his radio. All aircraft, new attack, profile is confirmed. We just dropped a fish at 300 miles per hour, and she ran straight and true. The morning briefings at Naval Air Station, Norfolk, painted a picture that no amount of official optimism could disguise. By March 1943, the TBF Avenger torpedo bomber had compiled a combat record that made seasoned naval aviators request transfers to literally any other aircraft in the fleet. Commander James Flatley reviewed the latest action reports from the Pacific Theatre, his coffee growing cold as the statistics told their merciless story. Avenger squadrons were losing aircraft at rates that exceeded 30% per mission during torpedo attacks against Japanese capital ships. The problem wasn't the aircraft itself, or the courage of the pilots flying it. The Avengers were rugged, well-armed machines that could absorb tremendous punishment and still bring their crews home. The fatal flaw lay in the operational requirements that turned every torpedo run into a slow-motion death sentence. Torpedo attack doctrine, unchanged since the Great War, demanded approach speeds of 150 miles per hour or less. At higher speeds, the Mark 13 torpedo would break apart on water impact or dive too deep to strike enemy hulls. This cruel physics meant that Avenger pilots had to fly straight and level at predictable speeds, while Japanese gunners had nearly a minute to calculate firing solutions and fill the sky with anti-aircraft fire. Lieutenant Commander Eugene Ewing studied the same reports from his cramped office at the Bureau of Aeronautics facility in Philadelphia. Where naval commanders saw an unsolvable tactical problem, the veteran aeronautical engineer saw physics that could be challenged. The Avengers Wright R-2600 Cyclone engine generated 1,800 horsepower, enough to push the aircraft well beyond 300 miles per hour in level flight. Yet operational limitations forced pilots to crawl toward their targets at speeds that made them easy prey for even the most poorly trained enemy gunners. The real issue wasn't the aircraft's potential speed, but the propeller's inability to operate efficiently across the extreme range of conditions that high-speed torpedo attacks demanded. Standard propeller designs of the era used constant speed governors that automatically adjusted blade pitch to maintain optimal engine RPM across normal flight conditions. These systems worked perfectly for conventional bombing missions or fighter operations, but they couldn't handle the dramatic power and speed changes required for high-speed torpedo delivery. At 300 miles per hour, a standard propeller's blades would be forced into such a coarse pitch that the engine would over-rev and destroy itself within seconds. The solution forming in Ewing's mind violated every principle of conservative propeller design that the Navy had relied upon for decades. Instead of limiting blade pitch, adjustment to the narrow range that existing constant speed systems provided, he envisioned a propeller that could shift from extremely fine pitch for maximum acceleration to extremely coarse pitch for high-speed flight, all while maintaining precise engine control. The concept was mechanically complex and would require hydraulic systems that operated under pressures far exceeding anything in current production. His colleagues at the Bureau of Aeronautics listened to Ewing's proposal with the kind of polite skepticism that innovators had learned to expect from established bureaucracies. Robert Stevens, the Bureau's senior propeller specialist, pointed out the obvious problems. The hydraulic systems required for such extreme pitch control would add weight, complexity, and countless potential failure points to an aircraft that was already carrying maximum combat loads. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Navy had invested millions in existing propeller technology and maintenance infrastructure. Retooling for an unproven system would delay production and potentially leave squadrons without adequate replacement parts for months. But Ewing had run the calculations obsessively during countless sleepless nights. A propeller system with a pitch range from 12 degrees to 45 degrees could allow an Avenger to accelerate from cruising speed to over 300 miles per hour while maintaining optimal engine performance. More critically, this expanded pitch range would enable pilots to decelerate rapidly after torpedo release, bleeding off speed before the aircraft's momentum carried it into range of enemy secondary batteries. The ability to both accelerate into attack runs and decelerate during escape maneuvers would transform the Avengers from suicide machines into survivable strike aircraft. The skepticism wasn't limited to the Bureau's engineering staff. At Curtiss-Wright, the company responsible for manufacturing Avenger propellers under Navy contract, senior engineers dismissed the extreme pitch range concept as a solution in search of a problem. Harold Mitchell, Curtiss-Wright's chief propeller designer, argued that existing constant-speed propellers were already optimized for the Avenger's mission profile. His alternative proposal involved minor refinements to blade shape and slight increases in pitch range that could be implemented using existing manufacturing tooling. The conservative approach promised incremental improvements with minimal technical risk and no disruption to production schedules. The Navy's Bureau of Aeronautics found itself caught between competing philosophies that reflected broader debates about innovation versus reliability in wartime procurement. The conservative approach offered proven technology with predictable performance and established logistics support. The radical approach promised revolutionary capability improvements, but carried enormous technical risks and the possibility of catastrophic failures that could kill entire aircrews. Admiral John McCain, tasked with evaluating both proposals as part of his responsibilities overseeing Pacific air operations, faced a decision that would affect thousands of naval aviators heading into combat against an increasingly desperate Japanese military. Meanwhile, across the Pacific, Japanese naval intelligence officers were tracking American torpedo bomber development with the same methodical attention they devoted to all aspects of Allied military capability. Commander Minoru Genda, stationed at the Imperial Navy's Technical Evaluation Center in Yokosuka, had personally examined several captured TBF Avengers. His reports to Tokyo were analytically precise and dismissive. The American torpedo bomber was a typical product of industrial mass production, rugged, reliable, and capable of absorbing battle damage, but fundamentally limited by outdated attack doctrine that made it vulnerable to even modest anti-aircraft defenses. Japanese naval gunners had developed simple but effective tactics for dealing with Avenger attacks. The aircraft's mandatory slow-speed approach meant that fire control solutions could be calculated with plenty of time for multiple salvos. The key was to concentrate fire at the 600 to 1,000 yard range, where torpedo-armed Avengers were committed to their attack runs and couldn't maneuver evasively without ruining their launch parameters. This confidence in existing defensive tactics permeated Japanese naval command. The Americans had proven they could build aircraft in staggering quantities, but they seemed unable or unwilling to challenge the fundamental tactical limitations that made those aircraft vulnerable to determined defense. The Avengers represented everything predictable about American military thinking: overwhelming force applied through conventional doctrine rather than innovative tactics or revolutionary technology. The February test flights at the Naval Air Station in Patuxent River would determine which philosophy would equip American torpedo squadrons for the crucial battles ahead. Ewing's extreme pitch propeller had been installed on a single TBF Avenger pulled from standard production for experimental evaluation. The aircraft sat on the flight line looking identical to every other Avenger in the Navy's inventory, but the propeller hub concealed hydraulic systems and control mechanisms that represented a complete departure from existing technology. Test pilot Lieutenant Commander John Bridges climbed into the cockpit with orders to evaluate the propeller across its full operational envelope and report any performance anomalies. As Bridges taxied toward the runway, neither he nor the engineers watching from the control tower could imagine they were about to witness the transformation of naval aviation's most dangerous mission into something that might actually give aircrews a fighting chance. The conventional wisdom that had accepted 30% loss rates as inevitable was about to be shattered by hydraulic systems and blade angles that would rewrite the rules of torpedo warfare across the Pacific. The first test flight on February 18th lasted exactly 11 minutes before Lieutenant Commander Bridges brought the modified Avenger back to Patuxent River with a troubling report. The extreme pitch propeller had functioned normally during takeoff and initial climb, but attempting to transition to fine pitch at high speed had created control forces that exceeded the strength of the hydraulic actuators. The propeller blades had partially shifted, but then frozen in an intermediate position that left the engine over-revving dangerously. Eugene Ewing watched from the tower as maintenance crews swarmed the aircraft, checking hydraulic lines and inspecting the propeller hub for signs of mechanical failure. The actuator problem wasn't entirely unexpected. Propeller pitch changes at high airspeeds created aerodynamic forces far exceeding anything experienced during normal operations. The original hydraulic system, designed for conventional pitch ranges, simply lacked the power to overcome these forces when pushing blade angles to the extremes that Ewing's design required. His engineering team spent the next 4 weeks completely redesigning the hydraulic actuation system. The solution required pumps capable of generating pressures 3 times higher than standard Navy propeller systems. This meant custom-manufactured components that couldn't be sourced from existing supply chains and installation procedures that would require extensive retraining for maintenance personnel across the fleet. Each modified propeller hub now weighed an additional 45 pounds compared to standard units, and the high-pressure hydraulic lines snaking through the engine nacelle added complexity that made routine maintenance significantly more time-consuming. The second test flight on March 23rd produced different but equally frustrating results. The redesigned hydraulic system successfully shifted the propeller through its full pitch range at high air speeds, but the extreme blade angles created cooling problems for the engine. The right cyclone cylinders, designed to be cooled by airflow managed through carefully calculated cowling arrangements, were now receiving inconsistent cooling as the propeller's varying pitch affected airflow patterns. Engine temperatures climbed to dangerous levels during extended high-speed runs, threatening to damage cylinder heads and exhaust valves. Robert Stevens at the Bureau of Aeronautics received these disappointing results with barely concealed satisfaction. His team had been advocating for the conservative approach, modest improvements to existing propeller technology that could be implemented, without the mechanical complexity and manufacturing challenges that plagued Ewing's extreme pitch design. Stevens forwarded his concerns to Admiral McCain with a memo suggesting that the experimental propeller had proven itself an expensive distraction from proven technology that was already saving American lives. But Ewing suspected the cooling problems resulted not from fundamental design flaws but from inadequate cowling modifications. The extreme pitch propeller changed airflow patterns through the engine compartment in ways that the standard Avenger cowling wasn't designed to handle. Working through spring nights in the Bureau's engineering laboratory, Ewing's team developed revised cowling designs with adjustable cooling gills that could compensate for the varying airflow conditions created by extreme pitch operations. The modifications required extensive changes to the Avenger's forward fuselage structure, but they would allow the engine to maintain proper operating temperatures across the entire flight envelope. The engineering challenges went beyond cooling systems. The extreme pitch propeller's ability to generate massive thrust at fine pitch settings created structural loads on engine mounts that exceeded original design specifications. Several test aircraft experienced cracked motor mounts during high-power acceleration runs, forcing Ewing's team to develop reinforced mounting systems that could handle the increased forces without adding excessive weight. Admiral McCain faced mounting pressure from Pacific Fleet commanders, who questioned whether the torpedo bomber program deserved continued investment in experimental technology. Combat losses were climbing as Japanese defensive capabilities improved, and some commanders argued that resources would be better spent on alternative strike aircraft or new torpedo designs, rather than attempting to fix the Avenger's fundamental tactical limitations through propeller modifications. The fourth test, flight on April 16th, finally demonstrated the extreme pitch propeller's revolutionary potential. With the revised hydraulic system, improved cooling, and reinforced engine mounts, Bridges pushed the modified Avenger through attack profiles that would have been suicidal with standard propellers. The aircraft accelerated from cruising speed to 280 miles per hour in less than 15 seconds, maintained that speed through a simulated torpedo run, then decelerated rapidly using the propeller's ability to shift into extremely coarse pitch for aerodynamic braking. The speed trials during simulated combat conditions produced results that exceeded even Ewing's most optimistic projections. The modified Avenger could execute a complete torpedo attack profile from initial approach through weapon release and escape maneuver in 43 seconds. Standard Avengers required nearly 2 minutes to complete the same attack sequence. The time reduction wasn't merely impressive from an engineering standpoint. It represented the difference between survival and death for aircrew operating in the most dangerous combat environment in naval aviation. But the most significant discovery came during high-speed torpedo drop tests. Navy ordnance engineers had been working parallel to Ewing's propeller development, modifying the Mark 13 torpedo to survive water entry at speeds far exceeding the traditional 150 mph limit. The modified torpedoes incorporated reinforced nose cones, improved stabilization systems, and stronger internal structures. When Bridges dropped a modified Mark 13 at 290 mph during the April 16th test flight, observers expected the weapon to either break apart on impact or dive too deep to be effective. Instead, the torpedo entered the water cleanly, stabilized quickly, and ran straight and true toward the target sled positioned 1,200 yards downrange. The Mark 13 struck dead center, proving that the combination of extreme pitch propellers and strengthened torpedoes could break the tactical tyranny that had made Avenger crews accept catastrophic loss rates as unavoidable. Japanese intelligence reports from early May painted the modified Avengers as an interesting but ultimately marginal development. Imperial Navy analysts noted that Americans were experimenting with higher-speed torpedo delivery techniques, but dismissed the modifications as incremental improvements to an obsolete attack doctrine. Commander Genda's assessment concluded that even with propeller improvements and faster approach speeds, American torpedo bombers remained vulnerable to concentrated anti-aircraft fire. Japanese naval gunners had proven their ability to shoot down attacking aircraft across a wide range of approach speeds and altitudes. The American modifications might reduce exposure time somewhat, but they wouldn't fundamentally alter the tactical balance that favored defending ships over attacking aircraft. The April test results convinced Admiral McCain to authorize limited production of the extreme pitch propeller system for operational evaluation. Curtiss Wright received a contract for 75 propeller units to be installed on TBF Avengers, scheduled for Pacific deployment in early summer 1943. The order represented an enormous gamble. If the propeller system failed in combat, the Navy would have diverted critical manufacturing resources away from proven technology, while aircrew paid the price with their lives. Ewing's team worked through late spring, preparing production tooling and training Curtiss Wright manufacturing personnel on the complex assembly procedures required for the high-pressure hydraulic systems. Each extreme pitch propeller required 60% more manufacturing time than standard units, and cost nearly 3 times as much to produce. The financial and logistical risks were staggering, but the text times of 92, potential payoff, reducing Avenger combat losses while improving strike effectiveness, justified the investment. As summer approached, the first production extreme pitch propellers left Curtiss Wright's factory bound for modification centers, where they would be installed on Avengers destined for carrier squadrons operating in the Pacific theater. Neither the American engineers who built them, nor the Japanese gunners who would soon face them in combat, could imagine how completely these hydraulic systems and impossible blade angles would alter the balance of power in the most dangerous mission profile in naval aviation. The first extreme pitch-equipped Avengers arrived aboard USS Essex on June 12, 1943, creating immediate controversy among the veteran pilots of Torpedo Squadron 15. Lieutenant Michael Grant, a survivor of 7 torpedo missions who had watched half his squadron die during attacks on Japanese cruisers, examined the modified propeller hub with undisguised skepticism. The external appearance differed little from standard propellers, but the maintenance briefing had revealed the complexity of the new hydraulic systems and the dramatically expanded pitch range. Several pilots questioned whether the additional mechanical complexity would prove reliable under combat conditions, particularly given the harsh environment of carrier operations, where saltwater corrosion and maintenance challenges were constant concerns. Squadron Commander Lieutenant Commander Edward Parker faced a delicate leadership situation. His pilots had survived months of brutal combat through skill and intimate knowledge of their aircraft's capabilities and limitations. Forcing them to fly unfamiliar equipment with radically different performance characteristics could prove fatal during the split-second decisions that combat demanded. But operational orders from Pacific Fleet Headquarters were explicit. The modified Avengers were to be evaluated under actual combat conditions as rapidly as possible. The success or failure of Ewing's extreme pitch system would be determined not in controlled test flights, but in life-or-death encounters with Japanese warships defended by veteran gunners who had been perfecting their craft since the war's opening days. The first combat mission for the modified Avengers came on June 19th during a strike against Japanese forces supporting operations in the Solomon Islands. Parker led a flight of 6 extreme-pitch Avengers in an attack on a destroyer and 2 escort vessels operating northeast of Guadalcanal. Standard doctrine would have called for approach at 150 miles per hour, giving Japanese gunners nearly 90 seconds to track and fire on the vulnerable torpedo bombers. Instead, Parker briefed his squadron on the new attack profile that Bridges had perfected during developmental testing. At 12,000 feet, well above the engagement envelope of Japanese light anti-aircraft weapons, Parker's flight formed up in loose formation and began their descent toward the destroyer. Instead of the gradual letdown that standard attacks required, the Avengers dove at steep angles while advancing throttles to maximum power. The extreme pitch propellers shifted into fine pitch configuration, their blades biting deep into the air and converting every ounce of engine power into forward thrust. Airspeed indicators climbed through 200 miles per hour, then 250, then touched 290 as the Avengers transformed from vulnerable bombers into screaming projectiles. The Japanese gunners, trained and experienced in tracking slow-moving torpedo planes, found themselves facing aircraft approaching at speeds that seemed impossible for heavy attack bombers. Their initial firing solutions, calculated for targets moving at 150 miles per hour, placed defensive fire far behind the actual position of Parker's formation. By the time gun crews could adjust their aim and recalculate firing solutions, the Avengers had already closed half the distance to torpedo release point. At 800 yards from the destroyer, Parker's flight released their Mark 13 torpedoes in near-simultaneous drops. The weapons struck the water at speeds that would have destroyed standard torpedoes, but the reinforced designs absorbed the brutal impact forces and ran straight toward their target. The destroyer's captain had approximately 8 seconds to recognize his vessel was under attack before 3 Mark 13s struck along the ship's length with devastating sequential explosions. Parker pulled his Avenger into a climbing turn while simultaneously shifting the propeller into extremely coarse pitch. The blade angle change created massive aerodynamic drag that bled off airspeed rapidly, allowing the aircraft to decelerate from nearly 300 miles per hour to 180 while climbing away from the engagement zone. This controlled deceleration was impossible with standard propellers and gave Parker's flight the ability to reduce speed before their momentum carried them through the concentrated anti-aircraft fire that Japanese escorts were now directing at the escaping bombers. The entire attack, from initial dive to escape climb, had lasted 37 seconds. Standard attack doctrine would have required nearly 2 minutes of exposure to enemy fire. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Word of the successful engagement spread rapidly through carrier air groups operating across the Pacific Theater. American pilots who had been flying suicide missions for months suddenly had a tactical option that didn't require accepting catastrophic losses as the price of pressing home attacks against defended targets. But more significantly, the extreme pitch propellers allowed Avenger squadrons to attack from positions and speeds that Japanese defensive doctrine wasn't designed to counter. Japanese naval gunners reported to their commands that American torpedo bombers were approaching at speeds exceeding 280 miles per hour, claims that were initially dismissed as combat stress or mistaken aircraft identification. The possibility that slow, vulnerable Avengers could achieve such speeds seemed to violate everything Japanese intelligence knew about American torpedo bomber capabilities. Commander Genda's Technical Intelligence Unit obtained its first detailed information about the extreme pitch system on July 8, when a damaged Avenger made an emergency landing on a small island held by Japanese forces. The aircrew successfully destroyed classified equipment and documentation before being captured, but the propeller hub remained largely intact for examination. Genda's initial analysis described the hydraulic system as grossly over-engineered and predicted that the mechanical complexity would create maintenance problems that would outweigh any tactical advantages. The detailed technical assessment that followed revealed the sophistication of Ewing's design in uncomfortable detail. Japanese engineers discovered that the propeller system incorporated hydraulic pressures and control mechanisms that exceeded anything in current Imperial Navy development. The pitch range, from 12 degrees to 45 degrees, was nearly double what Japanese propeller systems could achieve. Most troubling was the realization that the Americans had solved engineering problems related to high-speed pitch changes that Japanese designers had considered unsolvable with available materials and manufacturing techniques. Combat reports from July through September painted an increasingly grim picture for Japanese naval operations in contested waters. American Avengers were attacking at speeds that made interception by anti-aircraft fire extremely difficult. Loss. Rates for torpedo bomber attacks had plummeted from over 30% per mission to less than 8%, even against heavily defended capital ships. The tactical implications extended far beyond individual ship versus aircraft engagements. Japanese fleet commanders had positioned their major warships with confidence that American torpedo bombers represented a manageable threat. The extreme pitch propellers had transformed that threat assessment overnight. Capital ships that had operated with relative impunity in contested waters now faced attack from torpedo bombers that could strike with minimal warning and escape before defensive fire could achieve effective concentration. By October, nearly every frontline Avenger in the Pacific Theater had been equipped with extreme pitch propellers. The modification program had overcome initial manufacturing challenges and was producing propeller systems at rates exceeding 200 units per month. Curtiss-Wright's factories operated around the clock to meet Navy demands, with Ewing's engineering team working alongside production personnel to refine manufacturing processes and eliminate quality control issues. The statistical evidence of the extreme pitch system's impact became undeniable by autumn's end. Avenger squadrons equipped with the modified propellers reported a 78% increase in successful torpedo strikes compared to the same unit's performance with standard propellers. More significantly, aircrew loss rates had decreased by 65% as pilots gained the ability to both approach and escape at speeds that Japanese gunners couldn't effectively counter. The Avenger was no longer the most dangerous assignment in naval aviation. Admiral McCain received authorization in late October to expand the extreme pitch modification program to all Avenger variants in production and service. The success in the Pacific had convinced Navy leadership that Ewing's propeller system represented one of the war's most significant tactical breakthroughs. Orders went out to equip all torpedo bomber squadrons with extreme pitch propellers and to train all Avenger pilots in the high-speed attack profiles that the new systems enabled. Japanese naval commanders struggled to develop effective countermeasures against the transformed American torpedo threat. Traditional defensive tactics, based on tracking slow-moving targets with adequate time for fire control solutions, had become obsolete overnight. Attempts to concentrate anti-aircraft fire at ranges where Avengers had previously been vulnerable failed because the aircraft were now moving too fast to remain in optimal firing envelopes long enough for effective engagement. The transformation was complete, and irreversible. Eugene Ewing's extreme pitch propeller system had turned the TBF Avenger from naval aviation's most dangerous assignment into a strike weapon that could attack heavily defended targets with acceptable loss rates. The tactical balance of Pacific naval warfare had shifted decisively in America's favor, just as major fleet engagements would demand every advantage American forces could achieve. The Battle of the Philippine Sea, in June 1944, brought the ultimate test of Eugene Ewing's engineering revolution, as nearly 200 extreme pitch-equipped Avengers participated in the largest carrier air battle of the Pacific War. The massive strike force launching from American carriers at dawn on June 19th included more modified torpedo bombers than any previous operation. Their distinctive hydraulic propeller systems had transformed them from the most vulnerable aircraft in the Navy's inventory into precision strike weapons capable of attacking heavily, defended Japanese warships with unprecedented effectiveness. Lieutenant Commander Edward Parker led Torpedo Squadron 15's strike against Japanese carrier forces operating west of the Marianas. His 16 Avengers climbed to 15,000 feet with an authority that would have been impossible to sustain at combat weight with standard propellers. The extreme pitch system's fine pitch settings allowed the Wright Cyclone engines to develop maximum power during climb while maintaining optimal propeller efficiency. Below, the largest concentration of Japanese naval power since Midway was maneuvering to intercept American carrier forces. Above, American torpedo bombers were preparing to execute attack profiles that Japanese defensive planners had never anticipated and couldn't effectively counter. The Japanese fleet's response to the American strike revealed the devastating impact of the extreme pitch revolution on naval tactical doctrine. Vice Admiral Jisaburo Ozawa, commanding the Japanese carrier force, had positioned his fleet with anti-aircraft vessels arranged to create overlapping fields of fire against torpedo bombers attacking at conventional speeds. His defensive plan assumed that American Avengers would approach at 150 miles per hour, giving Japanese gunners adequate time to concentrate fire and create barriers of exploding shells that attacking aircraft couldn't penetrate without suffering catastrophic losses. The actual attack shattered these assumptions within seconds of the first torpedo drops. Parker's squadron initiated their attack runs from positions that Japanese commanders considered too distant for effective torpedo delivery. Diving from 15,000 feet while advancing throttles to maximum power, the Avengers accelerated to 290 miles per hour before leveling off for their torpedo runs. The extreme pitch propellers howled as their blades clawed through dense air at sea level, converting engine power into velocity that carried the heavy bombers across distances in a fraction of the time Japanese gunners had calculated for their firing solutions. Commander Toshio Abe, directing anti-aircraft operations aboard the battleship Yamato, watched in disbelief as American torpedo bombers approached his fleet at speeds he had thought impossible for such aircraft. His carefully orchestrated defensive fire plan, designed to create killing zones that slow-moving attackers couldn't survive, collapsed as the Avengers simply flew through the intended interception points before concentrated fire could develop. Radio calls between Japanese ships revealed confusion and frustration as gunners reported that American bombers were moving twice as fast as intelligence assessments had predicted. The morning's first wave of torpedo attacks developed across the Japanese fleet with coordinated precision. Multiple Avenger squadrons attacked from different directions simultaneously, forcing Japanese gunners to divide their attention and preventing the concentration of fire that had made earlier defensive successes possible. Lieutenant James Wilson's flight of 8 Avengers engaged the carrier Shokaku from an approach angle that standard doctrine would have considered suicidal. The extreme pitch propellers allowed Wilson's aircraft to accelerate from 200 miles per hour to 285 while descending through 3,000 feet of altitude. Japanese gunners aboard Shokaku's screening destroyers couldn't adjust their fire control solutions quickly enough to track targets moving at such speeds. By the time defensive fire began to concentrate effectively, Wilson's flight had already released their torpedoes and begun escape maneuvers. The Mark 13 torpedoes, striking the water at speeds exceeding 280 miles per hour, entered cleanly and ran straight toward Shokaku's exposed midships section. The carrier's captain ordered emergency maneuvering, but the high approach speed had given him less than 12 seconds between first visual contact with torpedoes in the water and impact. 5 Mark 13s struck Shokaku along her length, the sequential explosions tearing open fuel, bunkers and flooding machinery spaces. The carrier, veteran of Pearl Harbor and the Battle of the Coral Sea, would sink within hours. The statistical reality of Philippine Sea air operations told the story of Ewing's triumph in devastating numbers. American Avenger squadrons flew over 320 torpedo attack sorties during the battle, while suffering losses of only 17 aircraft, a loss rate of 5.3% that would have been unimaginable during earlier operations. Japanese fleet losses included 3 carriers sunk or critically damaged, with torpedo damage accounting for the majority of the lethal strikes. The extreme pitch propellers had proven themselves capable of delivering torpedoes with accuracy while keeping American aircrew alive through attack runs that previous doctrine had treated as one-way missions. Admiral Ozawa's evening report to Combined Fleet Headquarters painted a bleak picture of Japanese defensive capabilities against the modified American torpedo bombers. His gunners had claimed 43 attacking aircraft destroyed during the day's operations, but actual American losses were less than half that number. The extreme pitch Avengers had demonstrated the ability to attack from positions and speeds that rendered traditional anti-aircraft tactics largely ineffective. Japanese naval doctrine, built around the assumption that torpedo bombers were slow and vulnerable, had been rendered obsolete by hydraulic systems and blade angles that American engineers had perfected over 18 months of intensive development. The evening's final air operations occurred as American submarines and surface forces moved to intercept Japanese fleet units, attempting to withdraw from the engagement zone. Several Avenger squadrons conducted night torpedo attacks against Japanese cruisers and destroyers, using the extreme pitch system's ability to accelerate rapidly and decelerate quickly during complex night approach maneuvers. The timer, modified propellers proved essential for maintaining formation and executing coordinated attacks under conditions where visibility was minimal and collision risks were extreme. Eugene Ewing received reports of Philippine Sea operations at the Bureau of Aeronautics facility in Philadelphia, where his team was working to further refine the extreme pitch system based on fleet feedback. The success off the Marianas validated everything Ewing had envisioned when he first proposed his revolutionary propeller design. The system that skeptics had dismissed as over-engineered and unnecessarily complex had transformed American torpedo strike capability from barely survivable to devastatingly effective. The broader implications of the extreme pitch system's success extended far beyond individual battles. American naval aviation had gained a strike capability that Japanese forces couldn't effectively counter without fundamentally redesigning their entire fleet air defense doctrine. The ability to deliver torpedoes at high speeds meant that American carriers could engage Japanese fleet units from positions where defensive fighter coverage was minimal and anti-aircraft fire was ineffective. Japanese aircraft designers studying captured extreme pitch propellers in late June reached sobering conclusions about American engineering capabilities. The propeller system represented advances in hydraulic systems, materials science, and aerodynamic design that Japanese industry couldn't replicate with available resources and manufacturing capacity. More disturbing was the realization that the Americans had solved the fundamental problem of expanding propeller operational envelopes beyond traditional limitations. a breakthrough that would provide advantages in any future aircraft designs. As summer progressed and American forces advanced across the Pacific, the strategic impact of Ewing's engineering revolution became undeniable. The extreme pitch propeller hadn't merely improved the Avengers' performance, it had fundamentally altered the tactical balance between attacking aircraft and defending ships. Japanese naval commanders who had once positioned their fleets with confidence that torpedo bombers represented a manageable threat now found their vessels vulnerable to attacks they couldn't effectively prevent or mitigate. The transformation was complete and irreversible. The aircraft, once considered the most dangerous assignment in naval aviation, had become one of the most effective anti-ship weapons in the American arsenal, and the engineer who designed hydraulic systems and impossible blade angles had changed the course of the naval war across the Pacific. Japanese fleet commanders would never again enjoy the defensive advantages that had made their warships feel secure against American torpedo attack during the war's early years. The war's end found Eugene Ewing in his Bureau of Aeronautics office on August 15, 1945, reviewing production statistics that told the story of his engineering revolution in stark numbers. Over 8,000 extreme pitch propeller systems had been manufactured and installed on Avengers since that first experimental unit in February 1943. Each one represented a triumph of precision engineering that had required developing new hydraulic technologies and retraining thousands of maintenance personnel to service systems far more complex than anything previously deployed in naval aviation. Lieutenant Commander Edward Parker's final mission report from the Pacific Theater provided the human dimension behind those production statistics. His torpedo squadron, 15, had flown over 1,200 combat sorties with extreme pitch, equipped Avengers, delivering torpedoes against hundreds of Japanese vessels, while losing only 22 aircraft in torpedo attack operations. The loss rate of less than 2% per mission represented a complete transformation from the 30% casualties that had characterized early war operations. The statistical transformation of the Avengers' combat record revealed the true magnitude of what hydraulic systems and extreme blade angles had accomplished. Before the extreme pitch modifications, Avenger squadrons typically suffered one aircraft lost for every 3 successful torpedo strikes, an exchange rate that made torpedo bombing the most dangerous mission in naval aviation. After the modifications, that ratio had inverted to 3 successful strikes for every aircraft lost, turning every engagement into a decisive victory for American forces and accelerating the collapse of Japanese naval power across the Pacific. Commander Minoru Genda's final assessment, discovered in captured Imperial Navy files after Japan's surrender, acknowledged that American engineers had achieved a technological breakthrough that fundamentally altered the naval warfare balance. Japanese attempts to develop similar propeller improvements for their own torpedo bombers had failed due to inadequate hydraulic technology and manufacturing limitations. The extreme pitch propeller remained an exclusively American advantage throughout the war's final 2 years. The human cost of that advantage was measured in American aircrew, who returned to their carriers alive instead of joining casualty lists that had grown catastrophically long during early war operations. Lieutenant Michael Grant, who had scored his first torpedo strike with an extreme pitch Avenger during the Solomon Islands campaign, completed the war with 19 successful strikes against Japanese vessels and not a single loss to anti-aircraft fire during torpedo runs. His survival, multiplied across thousands of American naval aviators, represented the most meaningful measure of Ewing's engineering success. But the extreme pitch system's impact extended beyond individual survival to reshape the entire strategic character of the Pacific Naval War. Japanese fleet operations had become untenable by mid-1944, not because the Imperial Navy lacked ships or determination, but because American torpedo bombers could strike with such speed and effectiveness that defending vessels couldn't survive in contested waters. The extreme pitch-equipped Avengers had made Japanese naval operations so costly that major fleet units simply withdrew from offensive operations. The technological revolution that began with Ewing's unconventional thinking spawned an entire generation of naval aviation innovations. Subsequent torpedo bomber designs incorporated similar extreme pitch technology, and the hydraulic systems developed for the Avenger program found applications in countless other military and civilian aircraft. American aerospace engineers had learned that expanding operational envelopes through innovative propeller design could achieve results as significant as developing entirely new aircraft. Eugene Ewing's personal recognition came in the form of the Navy Distinguished Civilian Service Award, presented by Secretary of the Navy James Forrestal in a ceremony aboard USS Enterprise on September 2, 1945. The citation praised his revolutionary propeller system that materially contributed to American naval aviation's dominance across the Pacific theater. But Ewing knew that the real victory belonged to the thousands of American naval aviators who had flown his propeller systems into combat and returned safely to their carriers. Post-war analysis of Japanese naval defensive doctrine revealed how completely the extreme pitch revolution had disrupted enemy tactical planning. Captured documents showed that Japanese commanders had abandoned several promising fleet concentration strategies in late 1944 because they couldn't develop effective counters to American high-speed torpedo attacks. The psychological impact of facing Avengers that could deliver weapons at nearly 300 miles per hour had proven as devastating as the tactical advantages the propellers provided. The manufacturing legacy of the extreme pitch program extended far beyond naval aviation. American factories had developed high-pressure hydraulic systems and precision control mechanisms for propeller production that found applications throughout post-war industry. The engineering advances required for the extreme pitch system's reliability and performance contributed to improvements in industrial machinery, commercial aircraft, and eventually the helicopter industry that would dominate post-war rotorcraft development. The strategic lessons of the extreme pitch success were not lost on military planners preparing for potential future conflicts. The program had demonstrated that tactical dominance could be achieved through innovative application of existing technology rather than waiting for revolutionary new designs. American aircraft engines had always been powerful enough for high-speed torpedo delivery. The extreme pitch propellers had simply found a way to use that power more effectively across broader operational envelopes than anyone had thought possible. By autumn's end, production lines that had manufactured extreme pitch propeller systems were beginning to retool for post-war commercial aviation applications. The same hydraulic technologies and expanded pitch ranges that had given Avengers their devastating strike capability were being adapted for transport, aircraft, and commercial airliners. Ewing's wartime innovation was beginning its transformation into peacetime prosperity, promising to revolutionize civilian aviation just as completely as it had dominated military operations. The final measure of the extreme pitch system's success came from an unexpected source: interviews with surviving Japanese naval officers conducted during occupation. Imperial Navy veterans consistently identified the appearance of high-speed American torpedo attacks as the turning point when Japanese fleet operations became unsustainable. Commander Toshio Abe, who had survived the Philippine Sea battle and 4 subsequent engagements, described the extreme pitch Avengers as the weapon that ended our Navy's ability to operate offensively. Eugene Ewing closed his final wartime engineering report with characteristic precision, noting that the extreme pitch propeller system had exceeded all design expectations in operational service and demonstrated reliability superior to conventional propeller designs. Behind that measured language lay the reality of an engineering revolution that had transformed American naval aviation from accepting catastrophic losses as inevitable to achieving tactical dominance that Japanese forces couldn't counter. The propeller system that colleagues had once dismissed as over-engineered had proven that sometimes the most complex solutions produce the most decisive results. The war was over, but Ewing's revolution in propeller technology would continue shaping aviation for decades to come. The principles he had established, that operational envelope expansion deserved equal priority with raw performance, that mechanical complexity was acceptable when it enabled tactical advantages, and that radical engineering solutions often succeeded, where incremental improvements failed, would guide American aerospace development through the jet age and beyond. Hydraulic systems and impossible blade angles had changed far more than the survivability of a single torpedo bomber design. They had demonstrated the transformative power of engineering courage applied to problems that conventional wisdom had accepted as unsolvable. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.